up my appetite. Don't leave me high and dry. Baby, you give me ice and fire.
What is up, my internet chats? How are we all doing? And I say that with no one in the chat. Unless, babe, are you in the chat? As far as I can tell, you're not, but maybe she didn't get the notification. Come on, Twitch, you're failing me. But that's okay. Oh, I think she's in the chat now. There she is. Let's go. Okay, we got one viewer in the chat. My lovely wife, #1 fan. But we're gonna pretend like this chat is full because it's funner that way. So, what is up, guys? How's everyone doing? I had lunch a little while ago. I am in the chat. That's what she said. There's a little. Oh, I forgot to turn off latency again. Yeah, last time. We will talk about the mistakes made last time. Oh, she said I'm doing good. How about you? I'm doing good. Ate some ramen noodles for lunch. It was good. I put some egg and some butter. I will say, okay, here's the thing. It makes me this is such a big pet peeve of mine. Okay, it's not that big of a deal, but it drives me nuts when people are like, "Oh, you like ramen noodles? Have you tried putting an egg in it?" And everyone says that like it's the most unique thing ever. Everyone knows about that. Okay, if you're one of those people, sorry, but stop telling everyone to put an egg in it. Everyone knows it. Okay, it's not a new thing. I know it probably was new to you at one point, but you gotta stop telling everyone. It's embarrassing. Okay, I was one of those people one time too. And then I got a little bit older and I realized everyone knows about the egg and the ramen noodle. Stop being a hater, my wife says. But I will say, you guys like that? Look at this. I'm not sponsored or anything, just wanted to flex it there. Just kidding. It's just company I worked at. Okay, last thing about the ramen noodles though. I will say though, I've never heard anyone tell me this. Put some butter in it. It makes it so much better. It makes it like more creamy, more thick. Makes it more like not like I wouldn't say authentic. Obviously, not very good. This is just 10-cent ramen noodle, but it makes it like more creamy, like real ramen is. So I would say try that and put an egg in it. I'm not saying don't put an egg in it. Eggs are good. I put an egg in it. I'm just saying stop telling everyone that it's. Okay, anyways, pointless rant over. Who cares about my lunch? Let's talk about the stream. Okay, so there were some mistakes made last stream. One, I didn't know you had to wear headphones when you played audio because it would play through Twitch. Oh no, the Wi-Fi again. It's probably fine. I think it's back. The Wi-Fi is kind of being kind of crappy, so. Okay, she says it's good now. But I didn't know the audio could be played through both. So the last time I took that quiz, I was playing audio through my computer, which the mic was picking up, and it obviously plays the audio automatically to Twitch. So it was talking. It had that quiz. It had a little echo voice. It was kind of funny. It sounded like way more serious and powerful than I meant it to be. But so now I don't know if we'll use audio. I do have a quiz set up, but we'll see how much time the other activities take. We might not get to it today, but if we do, I got some headphones. Got that problem fixed. Second problem, it's gonna be the harder problem to fix, is my murmuring. I mutter way too much. And when I watched my video back, I realized it was hard to understand what I was saying sometimes. And so today, my goal for the stream is to talk more clear. I'll probably still mutter, kind of the same thing. But my goal is to be better and more clear, especially once I'm actually explaining some concepts today instead of just talking about me. So Second issue, I think I rambled too much, and here I am. It's already been 6 minutes, and I've already rambled a bunch. Already rambled about ramen noodles. But we'll see if I can be a little bit more focused, especially when we're talking about the topic. I think the topic I have a little more planned, so it'll be a little bit more organized. So yeah, I also, last thing that I fixed this stream. We had a sneaky viewer last time. I don't know who or when, but someone joined the stream. Okay, it wasn't just me and my wife watching for a little bit. But I didn't know because I didn't know how to see how many live viewers you have. And so he or she joined and disappeared without a trace. But today I got a little bit more. I got my Twitch stats up so I can see how many viewers I have. Which currently is just still 1. That's fine though. No biggie. And yeah. So now let's talk about actually what we're going to talk about today. As you can see from the title, we're going to talk about big O notation. You probably wonder what big O notation is. Or maybe you know what it is. Or I don't know what everyone's skill level is. But every time I hear big O notation, I don't know why I think of like the Mr. Beast, like, oh, thumbnail voice. Like big O. So every time you think of big O notation, I hope you think of that like I do. But in actuality, I want to go through what it is, why it's important, and how to kind of figure out some of the equations or the time complexities of certain things. So, oh, we're back, I think. Okay, one sec. I'm gonna open this door. Hopefully not let the Wi-Fi back. Sorry guys, I think I'm gonna try and disconnect the Wi-Fi. I don't know what happened there. Hopefully everything's okay. So, anyways, let's try to get through this stream with no more problems, no more disconnects. Cross the fingers. So big O notation, you might have seen people talk about the time complexities. They might share their code that they wrote on Twitter and how efficient it is and how time, and it's that ritzy ditzy like snobby kind of thing that is in coding. And that's how I always used to see it. It's just like, who cares, dude? Who cares how fast your algorithm is? Who cares how fast your coding is? Just for programmers to flex, for computer science nerds to talk about and flex. But I used to be like, who cares? It's not that important. Well, I was very wrong in that term, and I'm not saying it's still not annoying when people flexing their time complexities or, oh, I'm so good at programming. But it is very important, and I'll explain why in this video. So big O notation is just a way to measure how long it takes for a program to run the task it's been giving in context of how many inputs it's put in. Now, that might not make a lot of sense. There's a lot of big words and stuff, but let me explain it in an analogy I'm going to make here. So we're going to go over to web browser. We got Canva here. So we got Canva, and I'm going to explain. So let's just draw some stuff here. No, let's not do red. Let's do a different color. I don't like red. Let's do this green color. I like this green color. So we got big O. Okay. Love my writing. Great writing. We got big O. So let's say you wanted to start a company. Okay. And one of the important aspects of your company is you need to know how fast you could produce products, so that if you got orders, you could find out how fast you could produce them and ship them out to the customers. So let's say you're a robotics company. You create robots. Okay, let's go in here. Robot. Ooh, okay, what robots we want here? Let's get this guy. Oh my gosh, he's huge. Okay, I like this guy too. And why not this guy, dude? Nice little guy. Okay, so you got your 3 robots here, and let's say they all do a different task. Okay? Let's say this guy, let's just add text because my handwriting sucks. Say this guy sweeps oops. Let's say this guy cleans toilets. I don't even know if that's just about toilets. Who cares? You guys know what I mean. And then this guy, fine, I'll correct it. Toilets, it won't do it, so I gotta do it manually. Toilets, and this guy say this guy organizes books. Organizes books. You'd buy this guy. Guys, I'm a terrible speller. Deal with it. Organizes books. So you got these 3 robots, okay? Okay, so now you got to find out what it takes to produce all these. I'm just gonna draw the rest. I think it's actually easier. So let's say the sweep guy, his programming is very simple, and it just takes to build a sweep guy, it takes 10 minutes per sweep robot. 10 minutes. And for minutes. And let's say the toilet guy is a little bit more complicated, okay? He takes automatically 5 minutes to do the fundamentals. But then for every bathroom the customer has, the programming takes an extra, say 2 minutes per bathroom. So the bathrooms can represent n, right? So 2m plus 2m to the power times n. And let's say this book guy is really complicated, okay? Let's say his programming is just based on how many genres of books they need organized to the square root, right? So let's say it also takes 5 minutes to kind of build the show, plus n to square root, where n is the genres, right? So now you might think, okay, it's not that big of a deal. Let's say, like, if we were building, let's say if someone ordered one of each robot, you'll say, well, this one will take 10 minutes. This one will take 7 minutes. And this one will take, God, I really should have done this math before. 5 plus 2 square rooted is 4. This one will take 9 minutes. And so you might go, well, actually, surprisingly enough, the sweeps guy, the most simple one, takes the most amount of time. If you have 10, 7, and 9, well, then you say, well, I want 2 actually, and you'll see, okay, well, his takes 20 minutes. His will take. God, I didn't even do that math right the first time, guys. Sorry. Let me restart. Sorry. Cut that out. Okay. If you ordered 1, this guy would take 10 minutes. This guy would take 7, and this guy would take also 7. No, he would only take 6 minutes, actually. Because of the square root of 1 is 2, not 4. But if you ordered 2, then he would be 20 minutes. He would be, get my calculator out. That just makes it easier. Sorry, guys. This is embarrassing. I'm not a math major, okay? Don't judge me for not knowing math. So let's say 2 times 2 plus 5. So then this guy would take 9 minutes at 2. And this guy would take also 9 minutes. So all of a sudden you see these two equal the same at 2, which is kind of weird. You would think, what? Shouldn't they take the same? And this guy's still at 20 minutes, still the most. Well, what if we did 100? What if we had to have 100 of these? Okay. So 100 times 10, take 1,000 minutes. How many of this would it take this guy? 5 plus, so 100 times 2 plus 5 minutes. So it only take this guy, let's write these down. Take this guy 1,000 minutes to build, so the most still. It would take this guy 205 minutes. And it would take this guy, I have to do the math on the calculator. It's two big numbers now. Oop. Square root plus 5. And it would take this 10,005. Oh, this is a 5 minutes. So then you go, whoa, that's a big jump. This is now 10 times. It would take 10 times to make, 10 times as long to make 100 of these than it would to be these. And that's because with these equations, they have different growth rates when you add more and more product, right? And that's where big O notation is really important. On the low scale, it doesn't seem like it matters. Like, oh, who cares if one equation is... I mean, at the beginning, this was even the slowest one, right? But as this one grew, this one right here, this one gets significantly higher, and it's because of this specific thing right here, n squared. It's got an exponential growth. Well, not exponential, but a squared growth. While this has a linear growth, because for every one bot, you have, let me scroll up here. For every one bot, it equals exactly 10 minutes. But for this one, every one bot doesn't always equal, because if when you're at 1, this only equals 7. But that's incorrect. Not every one bot equals 7 minutes. Because of the more enhanced AI or programming you have to do, the more bots you put in, the more complex this gets. And so I want to flip over real quick to this right here, and this is an awesome page. It's called, right here you can see, I'll send in the chat. It's a big O cheat sheet. And it was created by this guy named Eric. You can go follow him on. I think this link takes you to Twitter or X, whatever you want to call it. I don't have a Twitter or X, so I can't go follow him. But as you can see, this chart demonstrates the different notations. So as you can see, the first robot is this one right here, O of n. So he grew linearly. You know, no matter how many you put 1 in, you get 10 out, and it will grow at a linear rate. While the other robot was this one right here, O(n) of squared, and he just progressively takes more and more time. And you can actually see when it comes to equations, that one's in the horrible category, and this one's in the fair category. And so you can see how this can be important for program. Like for example, in this business, you would learn, okay, this one is going to cost way more not resources, but time. I'm going to have to hire way more people to build these robots than this robot or this robot. And that's important. But when it comes to actual coding and programming, you can say, oh, okay, so if we want to implement this feature, if we put in big notations, we know that this feature is going to take a lot more time complexity than this feature, right? And so it helps when you're organizing and you're trying to figure out how to code things, it helps you understand in the long term. Because like I said, when I first started coding out, I'm like, what's the difference? Computers code things so fast that it doesn't really matter who cares if your program is a little bit slower. But it's not about on the small scale, it's about on the large scale how it can affect your thing. And so now I understand much more. But I want to go more in depth on these different complexities. So we have these complexities. We're going to go over a few of these today. But I want to do it in a special way. Hope you guys are excited for this because we're going to do it. Wait. Drum roll, please. In Minecraft. Let's go. So we're going to go over these time complexities and try to represent them in some things you might do when you play Minecraft. So we're going to go ahead and do that. So let's play. Oh, I just realized my volume's not on. I don't know how loud my desktop is, so hopefully it's not too loud. So let's go ahead and play some Minecraft. Yes, I use a controller, okay? I grew up playing Minecraft on the Xbox, so I'm a Bedrock player. But not only that, I'm also a controller because I used to play it on the Xbox 360 version back when the worlds weren't infinite. They were just like these tiny, not tiny, but they were a small world, and there was like a lot of nut features. So, but here we are. This little world I made. We are playing on creative mode to make this easier. So, okay. Yeah, my wife said, "Yeah, Minecraft, woo!" Okay, so we got our first notation is O of 1. Okay, and this one's a little complicated to explain. So we have here, we got a chest full of creeper eggs. Okay, and I'm sure you guys all know about farms in Minecraft. Let's say you want a creeper farm. I don't know if this is actually how you'd set up a creeper farm, but just bear with me. So we have these magnet cubes right here, and as we throw creepers in here, you can see, and now they don't fall. I didn't summon them all at the same rate, but they all die at the exact same rate. No matter how many creepers I put in there, they'll die at the same rate because they're all touching the magnet cube. Does that make sense? I could put like a bajillion in here, and they're all gonna die. Obviously I can't. I wish. I guess I could use summoning commands to summon more, and they'd all die at the exact same rate. But because they're independent of each other, they die at the same rate. And of course, if I put infinite creepers in there, or like a bunch, they wouldn't be able to all fit. But think about if you had infinite magna blocks with infinite creepers, they would all die at the exact same rate. And that's how O of 1 works. It doesn't matter how many inputs you put in, it's gonna be the same no matter what, right? Like for an example, like in a real life example of this is like, let's say whenever a user creates an account on Facebook, and I don't know exactly how their back end works. I'm not saying this is exactly how they do it. I'm sure it is, but they'll just add that account into the back end, and it doesn't take more time because they don't have to search through the thing. They'll just add it in, and maybe they sort it, so maybe that takes time. But imagine they have a place called new users, and it adds it in. No matter how many new users there are, it's only going to take however time it takes to put the new user in. And so that's a real life coding example, along with a Minecraft example of what O of n is. This one's fairly simple. This is kind of like, in a way, the gold standard of operations. This is obviously the best. No matter how many inputs you get in, it's gonna not take that long. But in reality, a lot of stuff you do will never be O of n because it takes time. There's certain things you have to do. And I guess I should say, looking back at that, let's go back to that chart real quick. Oh, I gotta pull it up though. Jeez, sorry. So like, this chart it has different sections like horrible, bad, fair, good, excellent. And obviously that's a measurement because you want to get your codes more in these areas. But in reality, sometimes there are certain tasks you want to do that even at the best case scenario, they are here. So, and one more thing I wanted to point out, Big O notation is measured in worst case scenario, okay? So like, if there's some variation depending on like for example, if you were looking, let's go back to Facebook analogy. If you were trying to look up somebody's username, right, through their database, you could get lucky and they could be the first person you find, or you could get incredibly unlucky and they're the last person you find. Big O notation is measured in how the worst case scenario, so how long it would take for you to get incredibly unlucky and find the last one. And it's measured that way because for worst case scenario, but it also is important to talk about the averages of certain algorithms and stuff like that, which we'll talk about more. So anyways, back to Minecraft. So, okay. So, now we got O of 1. Let's move over to the next one. Okay. We got O of n. Okay. So O of n, a lot of people call this the linear O of n, or they call it the linear equation. And that's because it moves in a linear fashion. So I would compare this to I'd compare this to like cooking something in a furnace, right? It takes the same amount of time to cook every piece of sand every time. So like, if this takes, I don't know how long this actually takes, but let's say it takes 1 second. Well, if you want to cook 64, it's going to take 64 seconds. If you want to cook 1 billion sand, it's going to take 1 billion seconds. It grows at a very linear rate. No matter how many inputs you put in, it has the exact same output. Hence O of n, right? N just equals the input. N is the input. So, yeah, so then that's how that works. The sand is equivalent to the linear O of n. And so in a real world example of this, and we'll just keep rolling with the Facebook example, is like, let's say you wanted to update every user inside of the database by giving them all. You wanted to put an exclamation point at the end of every user's in the database for whatever reason. Well, it would take, if it takes 1 second to put it on one user, it's going to take 5 billion seconds to do it to 5 billion users. It just makes sense because the algorithm or the task you've given the program will just go one by one and do that. And so that's another example. Okay, now let's talk O of n squared. Okay, so this is, remember on the chart, this is when you start getting into the bad, where it's going. And I like this Minecraft example because it shows how, this one I'm about to show you, it shows how sometimes there's no better way to do a task. So let's say your buddy tells you, hey, let's build a house, but dig out the floor, okay? So you go and you dig out a 4x4 square, or 2x2 square, right? That took like, a second to do by itself, really, really slow. But he goes, oh, that's not big enough. Make it 2 times bigger. So you go, okay. So you go, okay, 2 times 2, 4 times 2 is 4. So you go 4x4. So you go, okay, so it'll be twice as fast. Well, then you realize as you're doing this, it took 4 times as long. And you went, wait, well, that's weird. I only made it double as big. But not really, because we're working in squared, so you actually squared it, right? You could take 4 of these and put them in these 4, right? And then if you said double again, you're like, okay, 4 times 2 is 8. You do 8, but it would do the same thing. It would get much bigger. And after just a few times, you would be taking up huge plots of Minecraft land. But there's no real better way to do it. If you want to double your size of your house, you just have to dig it. It's just a fact. You can't get past, I mean, of course, you get redstone to do it faster or whatever. But the actual principle of it, it can't get faster. You just have to put in the work. You gotta put in that Minecraft grind, baby. So you can build that house made of diamonds. So that's O of n squared. And I'm trying to think of I had an example in mind, but it's adverting me now. But there are examples, I think, in programming. So if I think, sorry guys, I'm struggling right now. Oh, my wife's roasting me. She said, I said 4 times 2 is 8. You said 4. Oh, sorry. I meant if you wanted to double this, 4 would be 8. So times this by 2 would be 8. Not. I guess I said it wrong. My bad. Sorry, babe. I'm not watching the chat. I'm getting too into this. Anyways, let's move on to the last one. So this is kind of interesting. An interesting concept that you guys are going to have to kind of stick with me for me to explain this. And this is actually, this example is actually an algorithm, and I plan on covering this algorithm tomorrow more in depth. So you're going to see this analogy again if you join the stream tomorrow. But basically, sorry guys, I'm really parched now. Basically, this is an algorithm for searching to find things. And when I thought of that, I thought there was one thing you do in Minecraft you search for. It's the end portal, okay? Now imagine somehow, let's say you use your find your location command, but for some reason it's broken. So for whatever reason, it's between here and that point all the way out there, which is 100 blocks. I measured it out. Okay, by the way, it's O log n. Okay, that might kind of give away what it is. So let's say when we look, we only have 10 eyes right here, okay? So we need to get this exactly right. And let's say this is where the stretch part. Let's say you wanted to land exactly where the portal was. So you had to be on the exact spot it was. Okay? Well, there's a way. You might think, "Oh, well, just, throw one and then go this way, and throw one and go this way." But what if it was the very last, like we were talking about, worst possible situation. What if it was on the very last? This was the block you needed. And let's say the eyes of Ender didn't quite get you there. I know they probably would in reality because they traveled pretty far. But let's say, just for this analogy, this would only let you know one block at a time. So you would know, like, oh, this block. It would just tell you, let's say it would only tell you which direction to go according to the block. So, like, if I was on this block, well, let's go right here. If I was on this block and I threw it, it would move in one way, but I wouldn't know how far. I would either know it's in this way or this way. So let's pretend that's how it worked. And if it's in the very last section, you would definitely run out of all 10 of your Ender eyes. But there's something you could do. You could go to the dead middle, which I marked here for convenience, and you could throw it, right? Which I don't think I can actually throw it. But let's pretend I threw it. And let's say I threw it, and then it pointed this way. Okay, well now I've eliminated half of this, right? So now I only have to search. I went from 100 to searching 50. Okay, so that's a pretty good decrease, right? We cut the algorithm in half. Well, then we can do the same thing. We can go to halfway again, right here to this orange one. Okay, and then we can throw it, and let's say it goes this way again. Well, we've cut it down to half now. Now we're only to 25 squares, right? We can just keep doing that. Cut it to, let me get my calculator out again, guys. I'm not good with math. Sorry. One second, sorry. Okay, sorry. So we cut it in half. Oh, I was getting my calculator. Sorry, someone's texting me about something I need to take care of. Okay, so we're at 25. We divide 25 in half. We go down to 12. So let's say it's this way. So we'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh. It would be, I'd have to go to 12. So let's just go this way. So I'd be down to 12 left. So this is this already 12? Did I do the math? Yeah, 50, 25. That's the problem. I'm at 12 here. Well, actually 13, I think. 13. And we divide that by 2. Goes down to 6. So 1, 2, 3, 4, 5, 6. 2 again. Down to 3. 1, 2, 3. And then one more time would be down to 1. So we would find it specifically on this spot, right? Now you could say, oh, it was at the end, but that only took us, how many was that? 1, 2, 3, 4, 5. I believe it comes out, if you do the actual algorithm, it comes out to end up being 7 tries. So we only had to use at most 7 ender pearls. And what this illustrates is that this equation actually got slowly and slowly better. So if anyone knows math, log is the opposite of an exponent. So like log 2 is the opposite of to the power of 2. When that's what this is. This is essentially the opposite of this equation, right? This one grows at a exponential rate, while this one shrinks at an exponential rate because you cut it in half every single time. And so this one is like is actually the gold standard. If you can get your program to run like this, then you are a 10x developer. And that is kind of the goal. So with that said, a real life example of how you could use this. Let's say Facebook had all their users in alphabetical order, and they needed to find a specific user. Well, they could take their 5 billion users and go to the exact middle, right? Which would probably be in the K's. And they can compare that name to their current user they're trying to find. Like if they're trying to find, a guy named Joe. Well, K is G-H-I-J. How to do that? J-K. So K is after that. So they're at, if they had 5 billion, they'd be at 250 million. And so then they know, okay, well, he is in the first. If his name is J, if the dead middle is K, then they know that the user they're looking for is in the first 250 million. And so they went, oh, sorry, that's not right. 2.5 billion. They know that. So they just cut it in half right there. They went from 5 billion they had to search for to 2.5 billion. And that's a huge jump. So like searching through all those would take some time. And you can keep cutting in half. And I don't know the exact math of that, but you can see how a search like that is much more important. And we'll go over this tomorrow, but one thing about that is they call that a binary search algorithm, and we'll talk about that tomorrow more. But the one disadvantage of binary search algorithm is that it takes the list you're searching for, the things you're searching for have to be in order. So if it's like mixed up, binary search obviously doesn't work because you can't compare what you're looking for to the middle index that you pick. And so yeah, that's a few of the so what I'm looking for. Big O notations that are important. There's others that we'll go over. Oh, there is one more I want to explain. I couldn't think of a good thing to do this, but I'll explain it. And this is a prime example, even more than this one, of how no matter how good you are at programming, there are certain tasks that just can't be done any better way. So let's say you have 3 locations. You have these 3 locations. We can pretend these are 3 villages in Minecraft. Okay? Or let's put this more over here. And you wanted to figure out the fastest route between these 3. Okay? And let's say there's a road that connects all 3 of them. So let's connect these real quick. Excuse me. Oops. So we have a road that connects these. Okay. And then. Okay, so you have, these are terrible roads, but just pretend. Yeah, that looks a little better. So you have these 3 roads, and let's say you don't know where to start. You're not at one of these already. So you could say, okay, well, is the fastest route this one, to this one, to this one, to this one? Well, honestly, this one, it doesn't matter. Because once they're kind of in a triangle, it doesn't really matter because it's like a circle, essentially, right? But let's say we add a third path, right? And then this one connects all of these, right? And then, this has to connect. This road connects to all. And I'm not demonstrating this perfectly, but let's say there's roads that connect from all of them to all of them. So there's a road that connects these 2. There's a road that connects these 2, and there's a road that connects these 2. Likewise, there's a road that connects these 2, and these 2, and for that for all of them. Well, now it's much more confusing to figure out, to write an algorithm that can figure out which one to start at and which one to end at, because now you can go here to here, maybe over to here, then to here, but maybe this road's shorter, so you have to go here and here and here, and that you can just see how much more complicated that going with just adding one more. Now imagine if you added one more city and they connected to all of these again. You know, I'm not going to connect them, but imagine there's a road that connected this one to all the other paths. And you can see every time a new city is added or a new input, it gets exponentially harder because not only is a city added, but a road to each other city is added. So it grows at an exponential rate. And exponential is when you take like for example, the exponential growth of 4 is 4 times 3 times 2 times 1. And you can see that because when you have one, you have no roads. When you have 2, you have 2 cities and 1 road, so 1. And then when you have 3, you have 3 cities and 3 roads actually. 1, 2, 3. So now there's more. And then when you add another one, you add 3 more roads. So then every time you add a new city, you have to multiply it by the number of cities minus 1 because of it. And so it grows exponentially. Every city you add, and they call this problem in programming, it's been covered, and if you want to know more about it, you can look this up. It's called the traveling salesman. And to this day, there is no algorithm that we can find that is the best at finding the best path between these 2. Dude, my wife just said, she just said, and you get the longest road from... Me and my wife, we play a lot. My dad loves Settlers of Catan, and my wife, she loves to get the longest road. And she was just saying, once you build 5 roads, that's awesome. That's so funny. The longest road. Yeah. So then once you build 5 cities, you get the longest road, and you don't have to worry about the algorithm. No, but so even today, with this problem, the best notation we can get is O of n to the exponent. That little exclamation point. That means you times itself all by itself. That is the problem. So even genius guys way smarter than me, we have this problem, we cannot save it. And a lot of people a lot smarter than me think it is impossible to write a better algorithm than that for this specific problem. And this problem might sound trivial, but when you think about it, think about Google Maps. They have to, this is basically what they do. They have to try and find you the best route between, and they only do it between, most of the time, between two things, which isn't as hard. But if you have like a really complex route or something, you might have 3 or 4 things, and it just gets progressively more intense. And so yeah, it's something to think about. Hopefully you won't encounter anything too crazy like this. But those are my thoughts on big O notation. So, all right, let's go back here, just chatting. Okay, what time is it? Okay, we got about 10 minutes left. Let's go ahead and take the quiz. We're going to take a quiz. I don't think we're going to do lime juice or anything like that. We're just going to take a quiz on big O notation to see kind of how well this studying and stuff for this has given me. So we're going to switch over to, let me just get this set up. Oh, not that. I don't want to put that on full screen. I want to put that. So, okay, real quick before we jump over to the thing. So this is the notation I was just talking about for that salesman problem, or those 10 problems. N to the power, O of n to the power squared. You can see how that just shoots up, and that's the worst case scenario, but it is what it is. You can't be helped in certain cases. So anyways, unless it can be helped, you definitely don't want your equation to be doing that when it can be improved. So anyways, just kind of finishing thoughts while I get my headphones going here. Big O notation is important because it's a way to measure our algorithms, but also kind of our progress as programmers. I've spent some time on leak code, and leak code is measured by this kind of algorithm or this notation and how long it takes your thing to perform. And it's a good way to measure how well you are at doing things. And so anyone learning this, I'd encourage, one important thing is to try and read code and understand the most important thing. And I will say, coming over here before we take this quiz, it is important when it comes to big O notation. It's important to identify the most significant number in the equation. So you could have an equation like 10n plus 5 times n squared, right? That could be the notation of your problem, because those other notations, they don't always have to be exactly the other notations. They can be something like this, right, where there's actually 2 n's in here, right? Like you might have a programming code that one of the tasks it does this, and it takes 10 times n, but also it does this, which takes n to the square. Now, as you increase the amount of inputs, you will start to notice that the only really important part of the equation is this part. Because 10 times n, eventually, when you're putting in millions, doesn't make that big of a difference. But when you're putting in millions, n squared is. And so when it comes to notation, it's important when you're trying to analyze equations to focus on the n with the biggest significant difference. And that's one thing I took away from this new kind of study I've been doing of n notation, is it's mostly about which one is the most significant. And that's important because in your code, you can go back and say, okay, well, what's causing n squared in my code? And maybe you can optimize it and get the code down. over a long period of time. So, okay, let's take this quiz. Are my headphones in? Let's see. Just check if my headphones are connected. They are connected. Let's go. Okay. So hopefully this time, babe, you have to let me know if the audio on this video.
All right, welcome to another video.
If the audio on this video is too loud. Because I had it up earlier, it looked kind of loud, so.
And this time you're gonna be getting a quiz.
Oh, one last thing before we start. This is Tyler AI. I'm not sure. He does coding interview questions. Oh, geez, these are going to be hard questions. We're going to do bad on these. Hopefully this is a multiple choice. If this is not a multiple choice, I didn't want to watch it before so that in case someone is like, in case I didn't want to know all the answers before. So I'm going to go ahead and watch this. If it's like I have to solve things, we don't have that kind of time. Yeah, I just hope it's an A, B, or C quiz. And if it isn't, we're just going to call it good there. So
I'm not gonna give any hints or anything like that, but good luck. There's gonna be 5 questions, and there's gonna be about 10 seconds given each time. There's a countdown timer. Pause it, try to go through it, come up with an answer, and after all those are over, we'll go through them. All right, I'll see you shortly.
Oh. Yeah, this is like the exact thing of my channel I don't want to do. And I'll use this as an example, I guess. But as you can see, like, there's code here on the screen. You know, you got this int product, int a, b, a, b, int equals sum. And you know, it's pretty readable code. I'm not saying it's not. You know, it seems like you have a product. It's just doing math, right? You're adding sums. I believe this is Java. You're just doing an adding equation, but I just think in my mind, I think using analogies, not using code, is a lot harder. And this is what I'm saying. You should go in and analyze this code. And I'll go ahead and try and analyze this and see how well I do on the notation. But we're just going to do this one question. I don't feel like it's worth our time to do the whole thing. So int product, int a, int b, int sum. So basically what this is doing is this is they call it method in Java. In Java, where it takes in an integer, a number, 2 integers and a number, and then this is just the sum, and then for I, let I be less. So this is for every. I don't know why they're really doing a loop here. It's not really necessary. I int equals 0. I is less than b. I indent. Oh, okay. So it's adding the sum of all of a for every b there is. So if a is 1 and b is 3, you would add 3. You would basically do 1 plus 1 plus 1. And so the time complexity on that would be, it would be, in a sense, linear according to b, because for every b you put in, you would add a to itself that many times. So it would be a linear, because if you put in 1b, it would take 1 second. If you put in 2b, 2 seconds, b 3 seconds. Let's see how I did. You know, I'm still not the best at analyzing it. Could totally be wrong right now, but we'll see. The following computes a. What is the runtime? Oh, I guess I have. It's just giving me like, where are the answers at? Where are the answers at? Oh, he goes over them. Okay, we'll go over his video.
Each time. So really all we're doing is just going over this for loop of whatever b is. So the answer here is just big O of b. You can say big O of n, doesn't matter.
Yeah.
Just b is the.
So yeah, that's a linear equation. Big O of b, big O of n. That's the same thing. That's the cooking thing in Minecraft. How long you put it in. So, anyways, I think that was kind of helpful. I guess probably for some people to see the code, but not really the goal of my channel. I think sometimes staring at code can be confusing. You saw how much more I had to break it down to explain it. So, anyways, let's just kind of wrap things up. So, anyways, guys, thanks for watching. If any of you watch us on YouTube, no viewers today except for my wife. Love you, babe. But yeah, that's big notation. I hope it was a good way to explain things for those that are kind of trying to jump in this big notation, help people see why it's important and things like that. Hopefully it'll be nice to talk to my wife because she has a little background in computer science, but it's not anything she's pursuing for her for her career. So I want to see, coming from her perspective, how well I was able to explain it. And I'll say I did run through this one time with her, so she kind of already had a little precursor. But I did a much more better job, I think, explaining it this time. So yeah, watch on the YouTube channel. Go subscribe to Low Code Learning YouTube channel. I think there's actually two. There's already a channel. Look for mine. It's got purple and yellow lettering, just like the Twitch channel. And join us for our stream tomorrow. We'll be talking about binary search algorithm. It's a really good search algorithm, and it's kind of a good introduction to algorithms because it's easy to understand for the most part. We're going to do it again in Minecraft. Minecraft, baby. It'll be similar to how we did it in Minecraft, but it'll go way more in depth. So yeah, thanks everyone, and Godspeed.